Hey folks, and welcome back to Fermi Physics Solutions. This is the fourth episode in the Concept Explainer series looking at forces. So in the last video we looked at just different examples of balanced and unbalanced forces and how they affect the motion of different bodies. What I'm going to try and do is I'm going to try and link that now to what's called Hooke's law, which some of you may or may not have some sort of experience of. So I'm going to go through this, how I would explain this in the classroom to a bunch of students, and how I build it up, and then how I kind of reduce some of it down to make it more accessible for those students as well. So first off, the best way you'll kind of experience Hooke's law is with a spring. Hooke's law does have actually other applications outside of just things like springs. For instance, it actually works between the bonds in different atoms when you're looking at different types of solid structures, although that's something that you kind of would come across later on in much more advanced levels of physics and chemistry than what you'll do in second level. So for second level, you'll kind of focus just on simple objects like springs. So what I want you to do is I want you to just imagine that you take a weight and you attach it onto the spring. And it's got a decent bit of weight in the, weight. And just ask yourself, so I've just attached it on, but I haven't let it go. So that's literally the moment that they've been attached. And, I'm going to let go of that weight, and what's going to happen to my spring. And just give yourself a couple of seconds to think about that. And so what will happen is your spring will extend to a certain point, and then it will stop. And once you get to kind of this point here, the spring will kind of stay in a position where it's not going to be moving. So what we're going to do is we're going to look at the forces that happen just from the point when you let go of the spring to the point where the spring comes to a rest, even though it's been extended like it shows here. Realistically, this takes maybe even less than a second in real life, so I'm just going to use diagrams to kind of split it down the middle. Okay, just to be aware, there's two forces that we're going to be thinking about that are acting in this particular scenario. The first one is just the weight acting down, and we know what that is by the physical weight we add onto our spring, and usually you can read off the side of it. I'll tell you what that is. And the other one is the force acting backwards, or sorry, not backwards, but acting upwards, which in this case is the tension from the spring itself. Now there's going to be one particular point where we're going to rename that tension, and we're going to call that the restoring force. And that's what we get just at the end. And I'm going to kind of go a little bit more of that now in a minute. But just to be aware, when I'm talking about the restoring force, from a more like practical point of view, it is actually the tension of the spring. Just to be aware, just to save a bit of space, I refer to the weight in the future slides as Fw, and I refer to restoring force as Fr. Okay, so we're going to look at Hooke's law as applied to the spring, and we're just going to initially look at the idea of what happens the moment you actually attach the weight onto the spring, and then what happens just when the weight comes to a stop when the spring has extended and it's not moving anymore. Overall, this takes a matter of seconds or even just about a second to happen in real life, but we're just going to look at it as if it's a slow down approach. So the first thing we're going to do is we're going to add a weight. And when the weight is added, and this is literally the moment that the weight is on the spring, so there's the weight acting down, and we'll know what that weight is if we just read it off the side of the weight, usually 1 or 2 newtons depending on the make of the weights. They're kind of standard, and there's going to be a little tiny bit of tension already in the spring. And so what we'll notice there is that there is a much bigger unbalanced force acting down, because the weight acting down is much stronger in magnitude than the force of the tension acting up. So that's going to cause the spring to start to extend in a downwards motion. As it's extending, well, you have the same weight on it, because the weight that you've added hasn't changed. So again, whatever was written on the side of that is what's going to be. As the coil itself starts to expand, that's going to increase the tension. So as the coil is expanding due to the weight moving it down, that tension is going to keep increasing, and you get to the point where it stops moving, and at that point the tension in your coil acting up is going to be equal in magnitude to the weight pulling it down. So we go to this point where we have a balanced force acting on the coil, where one is the tension acting up, which in this case, if you notice, I've called the restoring force, or Fr, and that's equal in magnitude to the weight acting down. Why it's called a restoring force is if I were just to remove that weight from the bottom there, the force that causes the coil to move back up to its original position, so it would look like this, is the restoring force. So that's the force that the tension in the coil is trying to use to bring it back to its original position. And what we notice then is this is my start off point when I literally just added the weight. This is the end point where it's just come to rest itself. Again, this in real life only takes maybe even a second, maybe two. What I'm interested in is the very bottom of the coil and how much bigger it's gotten. So I usually have like a little red piece of plastic that I just attach to the bottom of my coil, and that red piece of plastic, as you can see, has moved down in this distance. That tells me what the extension of the coil is, and I'm going to use the letter X there. So what this diagram here is showing you is how do the forces acting on that coil in the spring change from the moment that you add the weight to the moment that the coil has come to its full extension and has stopped moving. There is a lot there, so I'm going to get rid of some of this. Right, don't need to worry about that for now. So the middle coil, I'm not worried about. There's also a lot of forces here. We don't need to know about them all, so I'm going to get rid of a few of these. So the two on the left are gone. So this now is just when I have my spring at its extension and it's not moving. And as we can see here, these arrows are equal in length, which means that they are equal in magnitude. They're the same forces. So let's just say that that's a 2 Newton weight acting down. That means that the coil has a 2 Newton restoring force acting up. Since I know those two numbers are the same, I'm only going to focus on one of them. So when I'm looking at Hooke's law, what I'm really looking at is the restoring force of the coil trying to pull the spring back up to its original position and the extension that it had from its original position. So they're the two real important variables that we need to think about: the restoring force and the extension. And how do we measure the restoring force? Very simply, the restoring force is equal in magnitude to the weight pulling down. So you read the number off this, it's the exact same force, it's just acting up. Okay, so if we look at just the spring when it's on its own, we can see, well, there's no weight added onto it. So if there's no weight added onto it, then there's no restoring force. So when I add a weight, what I know it's going to extend and then it's going to come to rest. And at that point, when the weight isn't moving up or down and the coil is no longer expanding, at that point, if I read the weight, I'll know what the restoring force is. So I'm going to call that, this is my first restoring force. So I have FR1, 1 for first, and FR for restoring force. So the restoring force is acting up. Again, I'll read that just from recording the weight number on the side of the actual weight, and the extension is just the difference in the length of the coil. So I'd measure this with a meter stick, I'd measure this with a meter stick, and I just find a different number. So if that was 20 and this is 25, take them away and that gives you 5 centimeters of the difference. If I add a second weight, and again these are identical weights, well, what I notice is there's more weight pulling down, which means I now have a stronger restoring force pulling up, and I'll have a greater extension again. So the more weight I add on, the bigger the restoring force is going to be, and the bigger the extension is going to be as well. That'll work up until the point where the weight is actually too much and it causes the coil itself to kind of get deformed. You'll notice if you ever just get a spring and you pull the spring to the point where it won't go back. The same thing happens with elastic bands. If you pull an elastic band too far, eventually it won't go back to its original position. So all of this is kind of working up until the idea before you reach that elastic limit, because after that you've damaged the equipment that you're using and it doesn't work the way you'd want it to anymore. Now I'm going to look at this with some simple numbers to give you better ideas. So again, here's just my coil with no weight added onto it. So again, there's no weight added on. The extension is also going to be 0. Okay, so then we take our spring and we will just add a weight, and as you can see, by adding the weight, that's caused the spring to extend. So if I read off the side of this one, let's just say it was a 2 Newton weight, so my first restoring force is 2 newtons, and let's just say I've used my meter stick and I've measured the length from here to here, and I've measured the length from here to here, and I found the difference. Then my extension is 4 centimeters. I then add a second weight, and by adding the second weight, I can see that I now have 4 newtons on it, and by putting 4 newtons on it, I am now up to 8 centimeters. Now I'm using very simple numbers. Being realistic in real life, you probably won't get the numbers to work out like this easy and this perfect, but I like the idea of showing you what numbers that you can do in your head. And then once you've done it with numbers you can do in your head, You'll use the meter stick, you'll get the real numbers, which will be more like decimals, and it won't always be doubles. It'll work the way it works, but the numbers will probably involve decimals. So then I take my 2 newtons and I add another newton or another weight onto it, and now I've got 3 weights added onto it. So every weight in this case was 2 newtons. So in that case, I have 3 weights, 2 newtons each. So that means that the restoring force is 6 newtons. So there's 6 newtons of that coil trying to pull it back up. And I'm going to ask you, based on what we saw just on the last 2 ones, what number do you think that's going to be? So when it was 2 centimeters, so when it was 2 newtons of restoring force, I got a 4 centimeter extension. When I got a 4 newton restoring force, that was the result of an 8 centimeter extension. So when you have 6 newtons, what number do you think should go there? And hopefully we've kind of seen the pattern now. When you have 6 newtons, you should have a 12 centimeter extension. So what we're starting to maybe notice is that for this particular coil, for this particular spring, that whatever weight you add, which will tell me what my restoring force is, the extension will just be double that number when you convert, directly from newtons into centimeters in this case. So if you just double this number, it gives you that one there. If you double the 6, it gives you the 12. I know they're different units, but just looking at the numbers for now, that's what it tells us. And then I'm going to look at the last one here, and this is the last one I'm going to do because obviously the screen is now running out of space. So there's 4 weights added onto my coil. So if I add 4 weights onto the coil, they're 2 newtons each. That means I have 8 newtons. And again, I just want you to think about in your head, what should that extension be now based on the pattern we saw before? So we saw 2 newtons was 4 centimeters. We saw 4 newtons was 8 centimeters. We saw 6 newtons was 12 centimeters. So what would you do to that 8 to work out the new extension? And hopefully what we saw there is that you will just, again, double the number because that's what you've been doing every time so far. So 2 times 8 is 16. So we're going to get 16 centimeters as our extension there. Okay. So you'll usually do some sort of setup like this in the lab. And when you make a table of your results, you end up with something that looks a little bit like this. So again, my restoring force was 0 because there's nothing added. So I'm going to get no extension because you had nothing on the first place. When I had 2 newtons added, my restoring force was 2 newtons. My extension was 4 centimeters. When I had 4 newtons added, I had a 4 newton restoring force, and that gave me an 8 centimeter extension. And what you can notice if you go every time here, it is you double these numbers. So 2 times 0 is 0, 2 times 2 is 4, 2 times 4 is 8, 2 times 6 is 12, 2 times 8 is 16. So every time you're doubling your numbers. You just double the number for your force, and that will give you the extension in centimeters. What does that tell us here? That tells us that when you put it on a graph, you're going to get what's called a straight line graph through the origin. The origin is this point here, the 0, 0. So it's the very corner where the x and the y-axis meet. It's a straight line graph because, as you can see, the graph is a straight line when you connect all these points. What that tells us is that whatever's on the y-axis is directly proportional to what's on the x-axis. So the restoring force is directly proportional to the extension of my spring. What does directly proportional mean? Well, it just means that whatever way you change your force, you do the exact same type of change to your extension. So if I have a 1 newton restoring force, that gives me a 2 centimeter extension. Well, what happens if I triple that? So 3 times 1 is 3, and 3 times 2 is 6. So that means by tripling my restoring force, I also end up tripling my extension. Do this for another number here. 2. So the 2 newton restoring force produces an extension of 4 centimeters. Well, what happens if I make that 2.5? So 2.5 times my restoring force. So 2 by 2.5 will give me 5. And that tells me I'm going to get 10. But those numbers work if you do it from here. So 2 times 2.5 is 5. And 2 times 2.5 times 4, it gives me the 10. Again, what direct proportional always means, whatever change you make to one is the same change you make to the other. I have 6 newtons here, and 6 newtons is going to give me an extension of 12 centimeters. If I half that and bring it down to 3, that tells me then I should half this number and bring it down to 6. So by halving 6, I get 3. Let's bring it across. I bring it to that line. I bring it straight down, and I do in fact get 6. So by halving my restoring force, I also halve my extension. Again, this is what direct proportional means. Whatever change you make to the force on the y-axis, whether you multiply up or multiply down, you make the exact same change to your extension here by multiplying up or multiplying down in the exact same way.